All right, now we're getting to some real fun stuff. So all the real heavy things that we were talking about with probability in the previous section, we're going to lighten it up now. We're going to work with some principles from combinatorics, and to work with things like random selection really effectively, we're going to need these tools because counting the number of possibilities can get really, really unmanageable. So, first of all, there's a couple of different essential items that we want to talk about here. So first, selection with replacement means things like coin flips, or if you draw a ball from a lottery spinner and then you put it back, or you can select letters for a password, right? So, for instance, let's think about, as an example, picking a password with 8 letters. You're allowed to repeat, okay? So if you're allowed to repeat, how many total possibilities do you have? What essentially you're doing is when you're setting your password, you can think about it as setting these spots. Is that 8 yet? No, that's 8. So your first letter, your second letter, and so on until you're finished. And for each one, how many possibilities do you have? Well, if there are 26 letters, well, okay, let's be precise. Let's say it's case sensitive, right? So uppercase A is different from lowercase a, and there's 26 lowercase and 26 uppercase letters, so you actually have 52. And then for the second, you can repeat. It can be capital A's all the way down, or lowercase z's all the way down. So your number of possibilities for each letter is 52. And by the multiplication counting principle, the total number of ways that you can do this is just multiplying all these all the way down. So in other words, the total number of possibilities for your password is 52 to the 8th power, which is roughly 5.35 times 10 to the 13, which is an astronomically high number. So, this is a very specific example, but if we're selecting with replacement, right? So, let's say there's n spots, or sorry, let's say there's k spots, n possibilities for each, or you're picking k items and there's n items total, then the total number of outcome or possible ways that you can select will be n to the k. So in this example, our n, our number of possibilities, was 52, and our k was the number of letters we were picking for our password. Now, if we want to talk about selection without replacement, now we're in another category. So, specifically, we'll talk first about arrangements. So when we talk about arrangements, what we mean is if we have n things, or let's say 4 people line up, how many ways can they line up? Well, you can think about it just as we did before, where we have 4 spots. For the first one, we have 4 possibilities because there's 4 people. So any one of them can be selected for the first one. For the second spot, we now have 3 because someone's already in the first spot. So we have 3 now. The next one down, now we only have 2 because we've already set aside 2 people. It's this idea of selection without replacement, right? So once we've picked somebody for a spot, they're no longer in our realm of possibilities, and that means that once you get to the third, or once you get to the fourth spot, the very last spot, there's just one person left. Which, if that is bringing up memories from getting picked last for kickball in elementary school, I'm so sorry. Same. So then, by the multiplication counting principle, we have 4 times 3 times 2 times 1 ways for people to line up. And we have a very special notation mathematically for factorials that represents this exact kind of calculation. So as a brief refresher or introduction if you're unfamiliar with factorial, we define n factorial, so it looks like an exclamation mark, to be n itself times the integer right before it, or the whole number right before, I should say, times the whole number right before that, all the way down the line until you get to 2 times 1. Okay, so as an example, right, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? So these can get really, really big very quickly because you're just multiplying by a larger and larger number. One really important thing to notice about factorial is that you can always break it up as n times n minus 1 factorial, or however many down the line you want to get. So to illustrate this, right, the same example. So 10 factorial is 10 times, and then the rest of it is just 9 factorial. So you can just split it up as 10 times 9 factorial. That'll be helpful later on when we work with other kinds of operations. Okay? So for example, how many ways can we arrange a standard 52 card deck? Well, when we say the word arrange, we're implicitly saying that we're just talking about n factorial, right? So the number of ways is going to be 52 factorial, which is 52 times 51 times 50 times 49, all the way down until we get to 3 times 2 times 1. As you might have guessed, this is an astronomical number. Roughly, this is about 8 times 10 to the 67th. There are more arrangements of 52 card decks than there are atoms in the known universe. It is an unbelievably large number. Now, we can use this for questions of probability. So let's say we arrange a 52 card deck, right? So what's the probability that the kings are all first? So in other words, we have our arrangement, so top to bottom if you want, and all 4 kings land in the first spots, right? So the probability of that, so let's call A the event in which kings come first. Then we're going to be finding the number of elements in this set divided by the number of elements in the total possible the total realm of possibilities. So that probability is going to be however large that set is divided by 52 factorial. Okay, so let's think about what that would have to be. So we're looking at the spots for our 52 card deck. So what do we have for the first four spots? So we know the kings have to land here, right? So we have 4 possibilities here, 3 here, 2 here, 1 here, right? Now, what about the remainder? So if that's how many possibilities we have, so 4 are selected, then 3, then 2, then 1, then that means that the next spot would have to be, we can only pick from the rest of them, which would be 48. Then there's 47 to choose, and all the way down to the very last one. Make sense? So then what we're talking about then is we actually are calculating 4 factorial times 48 factorial divided by 52 factorial. And remember that we said that we might find it helpful to split up the factorials in terms of their smaller nested factorials. So let's split this up into 52 times 51 times 50 times 49 times 48 factorial, and that's where we'll stop. So this is we're allowed to do this. And the reason why that might be helpful is because now we can cancel the 48 factorials. And so what we actually have is 4 factorial, which is 4 times 3 times 2 times 1, divided by 52 times 51 times 50 times 49. And if we calculate this, we should be able to find the probability of this event. So make sure you do your order of operations correctly. It is still a vanishingly small possibility. Namely, my calculator only goes out to 3.69 roughly times 10 to the negative 6, which is much smaller than the standard going out to 4 decimal places of precision. So for our purposes, we might say this is just basically 0. And if you're a little rusty on your scientific notation, this is the same as 0.000000369 roughly. So that's the probability of getting 4 kings turning up in the first 4 spots in an arrangement of a standard 52 card deck.